problem. So this is another example. A coil of 1000 turns is wound on a toroidal magnetic core having a reluctance of 10 power 4 ampere turns per Weber. So let's write the given data. So there is a toroidal magnetic core. So toroid means it's more like a circular core, something like this. And on top of this magnetic core, there is a coil which is wound. Okay, so it's covering the entire length of this one. Reluctance is so the reluctance of the magnetic path is 10 to the power of 4 ampere turns per uh, Weber. When the coil current is 5 amperes, so I is 5 amperes, and the number of turns is 1000, that is given in the question here. So I am using this data, and this data, and is increasing at the rate of 200 amperes per second. So not only current is 5 amperes, the rate of increase of current is 200 amperes per second. Okay, determine energy stored in the magnetic circuit. Okay, so first to determine the energy stored in the magnetic circuit, I need to find the inductance. Okay, so how do I find inductance? First, I have to find the flux. Okay, so total ampere turns. So we know that Ni is nothing but phi into R. So therefore, to find the flux, I can just do this. So ampere turns is 1000 into 5 divided by reluctance is 10 power 4. So 1, 2, 3, 4 ampere turns per Weber. Okay, so I think this 1000 will cancel, and then 5 by 10 is 0.5 Webers is the flux. And once I know the flux, then I can find the inductance L simply by doing N5 by I. So flux linkage is divided by I. So 1000 turns into flux is 0.5 Webers and the current is 5 amperes. Okay. So that is 0.1 and that will be 100 Henries. Okay. So this is about the inductance. So this seems to be very high number. Let me just check once again. Reluctance is 10 power 4 and the current 5 amperes. Okay, let me check the calculations here. Okay, I think this all seems to be correct. So now energy stored in the magnetic circuit. So for energy stored in the magnetic circuit, I have to do half Li square. So that is half into 100 into I. So my current is 5 amperes, 5 square. Okay, so that is 2500 divided by 2. Okay, so that is 1250 joules. Okay. So this is the energy stored in the coil. Voltage applied across the coil. Assume coil resistance as 0. So some voltage needs to be applied across the coil. So I'll just show that voltage, and so that the current is 5 amperes. Sorry. Yeah. So and the rate of change of current di by dt is 200, that is given. So how much voltage will be induced in the EMF? So that we'll have to see. So induced EMF is minus L di by dt. So that is minus 100 into 200 per second. So that is nothing but minus 20 kV. Okay. These all values are coming quite different. I think there might be some problem in somewhere in the data itself. Let's continue. So, how are your answers affected if the coil resistance is 2 ohms? Okay, if there is a 2 ohm resistance here, how the uh, how the answers will be affected? See, as far as the coil is concerned, inductance is going to be the same. So this flux will be same, inductance will be same. Only thing is at the time of calculating induced EMF, I will also have to account because there will be some voltage drop here. I think 10 volts will be the voltage drop here. That much voltage drop I have to add to the answer to that to get my supply voltage. So it will be the answer for the third part will be minus 20 kV plus 10. So something like this. Yeah. So I hope you got some idea in it. These values are coming very high. Might be some problem in taking down the data. So, but then this is the procedure to solve the question. I think we'll see more problems.